Let's talk about how do we graph a rational function here. So we're given 4x squared over x squared minus 9. And over here I have a couple of details labeled for some of the important things that we want to find in order to help us graph this rational function. So one of the first things we're going to do here, in order to find the y-intercept for your graph here. So let me go ahead and draw this out a little bit here. So if we're going to find the y-intercept, to find the y-intercept of any function, you want to evaluate f of 0. So plug 0 into your function here. So that's going to look like 4 times 0 squared over 0 squared minus 9. Well, we're going to get a 0 in the numerator there, multiplying by 0. This is going to cancel out down here as well, leaving us with a negative 9. 0 over any number is a 0. That tells us that our y-intercept, also an x-intercept here, is going to be the point 0, 0. Now, our next step here, we do want to check to see, are there any x-intercepts in our function here? So in order to find the x-intercepts of a rational function, what you want to do is you want to take the numerator, set it equal to 0, and solve. Now, if we take the numerator, set it equal to 0, and solve here, we're going to see that we're going to end up with 0. Right? Divide the 4 on each side, gives us x squared is equal to 0. Take the square root, we still get x is equal to 0. So that means this point 0, 0 over here that we found for the y-intercept is our y-intercept and our only x-intercept as well. The next thing that we typically look at then is finding the vertical asymptotes of our graph. In order to find the vertical asymptotes of our graph, what you want to do is you want to take the denominator and you want to set that equal to 0 and solve that. All right, so we're going to take our denominator, which is x squared minus 9, and we're going to solve this by adding 9 on each side, giving us x squared is equal to 9. Taking the square root of each side gives us that x is equal to a plus or minus 3 there. So that means that we have vertical asymptotes over here, one at a negative 3, and then one at a positive 3 here. One of the last things here we're going to find then is our horizontal asymptotes, to see if we have any of that. Now, the way that horizontal asymptotes works in order to figure that out is you want to look at the degree of your function, specifically the degree of the numerator, the degree of the denominator. If you look at your numerator, our degree for our numerator is a 2, right? The highest exponent, our highest power here. So we have a 2 for our numerator. We also have a 2 for our denominator. And the rule for horizontal asymptote says that if the degrees are the same, which they are in this situation here, your horizontal asymptote then becomes the division of the coefficients in front. In front of our numerator, x squared, we have a 4. In front of our denominator, x squared, we have a 1. Right, so 4 over 1, which is just a 4. That means that we have a horizontal asymptote on our y-axis over here at a positive 4. Now, after going through and finding the 4 different things here, our x and y intercepts, our vertical and horizontal asymptotes, this is what I currently have on my graph. And if you take a look at that, we only have 1 point here. Now, kind of just understanding things about rational functions, I can assume here in my middle section, from this point, we are not going to want our graph to shoot upwards because it's boxed in by all of these asymptotes. It's going to want to shoot downwards here. And I'm going to assume that this is going to look like a parabola that's going to shoot down. But when it comes to math, we never assume. At this point here, in order to wrap up our graph, we do want to find additional points simply by plugging into our function here. So I'm going to plug in a few points, starting with a negative 1. If I plug in a negative 1 for x here and simplify this, right, I get a 4 up top, and I get a negative 8 down bottom, which leaves me with a negative 1/2. That means when I plugged in a negative 1, I got a negative 1/2. So I do get this point here. If I plugged in a positive 1, this would actually end up being the exact same thing, just because if you see here, our x's are squared, so whether it's negative or positive, they're going to end up being 1. So when I put in a positive 1, I also get a negative 1/2, which just tells me I have the point 1 and a negative 1/2. Which means that my graph is doing what I assumed it to do. We do have a parabola here, and we can go ahead and connect those dots. We know our graph wants to be near those asymptotes, and it's just going to keep following those lines here. That kind of takes care of this middle section for our graph. So now I want to know what it's doing on either ends over here. So what I'm going to do at this point here is I'm going to find a point on either side of these vertical asymptotes that I have. So that means I'm going to choose a -4 and a +4. I'm going to plug that into x. We are going to see the same situation as we saw with the -1 and a +1, where we are going to end up getting the same exact values here. So when we calculate this, -4 squared, so 4 times 4 is 16, and 16 times 4 is a 64. And our denominator, 16 minus a 9 is a 7. So when we divide this out here, we're left like a 9 point something. What that tells me, so let's see, a 1, 2, 3, 4, 5, 6, 7, 8, 9. That means when we plug in a -4, we are getting about a 9 point something, which also means if we plugged in a +4, we would also be getting that point here. Plugging in, just maybe finding one more point here, we can test a -5 and a +5 here. So by plugging in a -5 here, I went ahead and plugged in a -5 and I got a 6.25. So if I plot that here, -1, 2, 3, 4, 5, and then a 1, 2, 3, 4, 5, 6. I'm seeing it about here, which I'm going to mirror that on our +5 over here, 1, 2, 3, 4, 5, and our point like this. Connecting these dots gives us this shape here. We can see that they're curving, right? That means that our graph is kind of doing what it tends to do with asymptotes. It is going to continue to hug these lines and continue moving closer and closer to those asymptotes. So this is a very good idea here of what this rational function looks like.